Kristine and I were betting at breakfast about how many people would be here, and we underestimated the group, so thank you all for coming. This is a topic that I guess I learned about the hard way when someone came in to my office and said, you know that paper you're writing, well, the econometrics are a mess. The background is that fixed effects have become a pretty big and important way of controlling for unobservable heterogeneity in data. And as long as the data panel is not dynamic, as long as it's static, that's pretty much okay. But as soon as it becomes dynamic, as soon as you think that last period's behavior or values affect this period's values in the dependent variable, then everything goes off the rails econometrically, and you need to be very careful about what you do. So when we started out doing this paper, we had in mind sort of Mitch Peterson's paper about standard errors, not that we thought we were going to replicate it, but it was our model that Mitchell went and identified a set of econometric issues that almost everybody has to deal with. This is not so broad. And then he sort of explained what the problem was, and he explained, practically speaking, the best way to approach the problem in actual data. And we're trying to do the very same thing. The Wintake paper et al. that we've got referenced here is about the effect of corporate governance on firms' performance. Now, personally and secretly, I've always thought that corporate governance was endogenous and that I didn't know which way the causality went. And that's largely what this paper's about. What they say is that historically, people have looked at the correlation between corporate governance and contemporaneous firm performance. And some people have found positive relations, some people have found negative relations. And this paper goes through sort of the endogenous relationship among the variables, explains the econometrics, does a very nice Monte Carlo study, and then winds up concluding that the effects are zero. So the important point about that, you should read the paper if you're interested in these econometrics. The important point about it, though, is that what methodology you use to estimate a model matters. It's going to make a material difference, potentially, to the inferences that you draw. Let me say, again, I should have said this at the start. If you've got clarifying questions, please interrupt at any time. Interrupt Kristine in particular. But we've tried to clock this so that we'll get done in maybe 45 minutes, and then we can have up to another 45 minutes for more general questions. But certainly clarifying questions, please ask those anytime. Now this Gormley and Matza paper is talking about how to control for unobserved heterogeneity. Actually, the title of the paper is How or How Not to Control. So they find a lot of ways that do a bad job. But they wind up recommending fixed effects models as a very good solution to unobserved heterogeneity. Now they're working in static models, non-dynamic panels, and so their fixed effect estimation is very straightforward. But if you take their recommendation and put it into a dynamic model, then we're back into this Wintake et al. Sort of world where the estimation method you use can have a material effect on what you conclude. If you think about places where dynamics have come about and are used in finance, you can think about payout policy, you can think about capital structure, you can think about the relationship between cash flows and investments, where maybe investments have some sort of dynamic process. You can look at corporate governance, as the paper I just talked about. And then there are a bunch of papers, as I'm sure many of you know, that try to connect financial conditions to financial development, financial growth in an economy. And there too, you might think that things don't change all at once, that there's some dynamism in the relationship. And so you might wind up using a dynamic panel across, in that case, many countries. So there are lots of places that you can think about applying these models, these estimation methods. Kristine and I have this paper that's forthcoming, and this forms the basis for what we're going to talk about today. More importantly, perhaps, the slides and a bunch of background readings are on Kristine's website. So I'll leave that up for a second so you can jot that down, because we didn't think to put it on the last slide, which probably we should. But there you'll find a link to the paper, you'll find the slides, you'll find some background reading. And so if you're interested in this or feel you need to know about it, that's a pretty good place to start if you're starting out. So let me explain first where the problem comes from. This is what my colleague explained to me when he said, oh, you're doing a terrible job here. If you think about a dynamic panel model, there's a dependent variable. I've left out the coefficients. There's a dependent variable regressed on the lag-dependent variable, and some explanatory variables, and a fixed effect, which is a 1 for this firm and a 0 for all other firms, and a residual. Well, the trouble is that because y is a function of the fixed effect, so too is lag y a function of the same fixed effect. And so the lag y has a residual in it that winds up being correlated with the fixed effect. Okay, you can think of the fixed effect as taking out the average residual from what you get if you ran an OLS regression across a bunch of panel data. So the fixed effect essentially includes the average of some of the unexplained variation about the ith firm. And some of that unexplained variation is in the residual of that. So we have some correlation. We have some correlation, and that's going to give biased estimates if you were to just run this as sort of an OLS without any instrumentation. The problem is, you might say, well, okay, so let's throw out the fixed effects. You can throw out the fixed effects, but the fixed effects turn out to be important in a lot of models for capturing unexplained time-consistent heterogeneity. So your choice is either misspecify the model or deal with the correlation that is induced by having a dynamic panel. And again, let me emphasize that if this were not dynamic, if this variable is not here, no problem. But with the variable there, it turns out to be very important. Now, there are a couple of ways you might say, well, gee, let's look at that. Let's look at that equation and let's just get rid of that fixed effect. If that's the problem, let's get rid of it. One way to get rid of it is to demean all the variables. And some of you, I'm sure, will recognize that this is sort of a poor man's fixed effect estimator. But if you demean the variables by taking, for the ith firm, taking out its average value of all the y's and its average value of all the x's, you're still going to have a correlation between the demeaned residual, the mean residual out here, and the residual component in here. So if you've got 5 firms in your panel, then this average residual out here is an average of 5 errors, one of which is in here. So you've got the correlation, and that also sort of looks ahead to make clear that the bigger is T, the longer is your panel, the less important is this bias. Because the longer is your panel, the less this average error has to do with the one that's in the equation on the right-hand side. So if T goes to infinity, this goes away. Unfortunately, if n, the number of firms you have, goes to infinity, so n times T, T is the panel length, n is the number of firms. If n goes to infinity, it doesn't help you at all. But if T goes to infinity, it does. It's just that the average firm, for example, on CompuStat is there for about 11 years. So T is about 11 for the average firm on CompuStat. So demeaning doesn't fix the problem. It gets rid of the fixed effect, but it sort of moves the problem. You can also first difference, which is where the GMM estimators start. You can also first difference, but now you first difference out the fixed effect, but you still have this correlation between the lag-dependent variable and the lag residual. So you can't get away from it. The correlation still exists. Now, is it important? Well, the answer is yes, it can be really important. So here's an example that was actually in Kristine's dissertation, where she estimated a leverage model, capital structure model. MDR is the market debt ratio. X is a bunch of explanatory variables. F is the fixed effect. Now, if you estimate this equation for firms that have short panels, and then you estimate the same equation for firms that have long panels, you might say, well, that'll give me an idea of what kind of bias is associated with short panels. The trouble is that those firms that have long data series are probably qualitatively different from the firms on CompuStat that have short data series. So in order to try to focus on what the panel length does to the estimator in this context, she took all of the firms on CRISP and CompuStat that have 30 years of data and ran that regression once for however many firms there are that have 30 years of data. Then she said, well, let's take each firm's 30 years of data and let's sort of artificially split it into three and pretend that we have three different firms. Same data, but three different firms with 10-year panels each. So what we did was we cloned or expanded the number of firm identifiers. And then next step, do it with 5-year panels. Same data set, do it with 5-year panels. And if you estimate the 30-year panels, you get an adjustment speed out of the OLS of 13%. Well, that's misspecified, leaves out the fixed effects. The fixed effect estimator gives you an adjustment speed of 25%, which is sort of the ballpark of where capital, trade-off model capital adjustment speeds are in the literature now. But if you take the same data and you shorten t, so you increase the seriousness of this simultaneity bias, then you get an estimate of the fixed effect adjustment speed of 44%, or 66%. So how long that t is, how long the sequence for each firm, how long the panel is, turns out to be really important in terms of what estimate you get. Now, one of the estimators that we're going to say is pretty good is the one by Blundell and Bond, 1998. And that estimated speed of adjustment is 15 to 18. Varies a little bit with panel length, but not very much. So it's easier to believe that the true adjustment speed is something like 15% than that the true adjustment speed is either 25 or 44 or 66. That's a much more helpful answer, of course. So you've got a bias with the dynamic panel, and the bias is important. You got to deal with it. How can you deal with it? Well, you can ignore it. I've already said that's not a very good idea. You can instrument for it. What econometric problem is there that can't be solved if you have appropriate instruments? The trick, of course, is finding instruments. Then the GMM estimators came along, starting in the late 80s. And if you've looked at this literature at all, you know the names Ariano Bond and Blundell Bond, and you may know about this more recent Hahn estimator. And what these guys are doing is they've essentially recognized that they can use lagged values of the dependent variable and lagged values of the x's, the explanatory variables, as instruments for the current value. And that's what the GMM thing is about. That's what the GMM is doing, is it's making up some instruments that have statistical validity, and you don't worry particularly about making the kind of instrumental variables argument you always have to make. It's correlated with this, it's not correlated with that. So instead, they just have statistical validity. Now, when I started out, I didn't know much about GMM. So the GMM estimators are all driven off of a first differencing. Okay, they try to get rid of the fixed effect by first differencing. And so what you want is an instrument for the lag difference. And what Ariano and Bond point out, what they derive, is that you can use the lagged levels of the variables as valid instruments for the difference here. So they use the lagged levels to instrument for the differences. The bad news about that is that if you've got second order or higher serial correlation in the residual, then using lag values is going to be, the lag values are going to be correlated with the included variable, and they're not going to be legitimate instruments. And that's something that we tested, what's the seriousness of that sort of bias. Blundell and Bond, a couple of years later, 1998, I think, say, well, look, it also turns out that the lag differences are legitimate statistical instruments for the levels. So they have a two-equation system where in one, they do what Ariano Bond did in one equation, and the other equation, they instrument for the levels of the variables with the first differences, lagged first differences. And then this long difference estimator came along in 2007, and Rungbing Huang and Jay Ritter had a JFQA paper where they executed this. And the long difference essentially says Ariano Bond and Blundell Bond have a problem if there's serial correlation. So what we'll do is we'll look at really long differences instead of 2 period differences. Use 2 periods ago level variable to instrument for the difference today. These guys are saying we'll use way far distant differences in order to instrument for the differences today. And that way we get away from this concern, among other things, we get away from this concern about short-term serial correlation. So when they derived, Kristine and Hausman, I guess, when they derived their estimator, they did it in an environment where the panels are all balanced. Well, as you know from CompuStat, the panels are not all balanced. So what Fong and Ritter did was they said, well, let's use 4 period differencing because that'll let us use a lot of variables. That'll let us use a lot of firms. And it's consistent with the spirit of long or longest differencing. So what we're going to do is we're going to, and the other thing that Fong and Ritter had to deal with is the fact that the panels are not all of the same length. Okay, so using a 4 period difference also allowed them to include a larger number of firms. As a matter of theory, they know this, as a matter of theory, nobody knows if that's really a reasonable representation of what the Han people did. And what we've done is we've implemented the longest differencing interval in these variable length panels by just taking the longest difference that's available for each firm. And then we got Rongbing's static code to implement this LD4, long difference 4 estimator. So if you're familiar with that paper in the JFQA, which won, I forget what the name of the prize is, but it was the best paper prize for 2009, then you know that that's what they've done. They've used an instrumental, they've used GMM method for instruments. So in terms of the solutions, we don't really want to ignore. We've got a bunch of instrumental variable approaches. And then in 1995 and further developed in 2005, there's a way to explicitly look at the data and correct for the bias that's associated with this correlation that causes the trouble. So this Kvyat and Bruno approach is in status called LSDVC, least squares dependent variable corrected. The trouble with that is that it needs all of the data in RAM at the same time. So for, what did you say, 15 or 20,000 observations is about the biggest that your computer would do? Somebody has a bigger, there's always a bigger computer. And so the fixed effect thing, you want the fixed effects in there because of the heterogeneity. You got to worry about the bias to the adjustment speed and therefore the possibility of bias to the other explanatory variable coefficients. Instruments are traditionally hard to find, or traditional instruments are hard to find. GMM is explicitly based on there being no second order serial correlation. We don't know about long differencing in unbalanced panels. We didn't know anything. And the LSDVC assumes that the explanatory variables are exogenous, not just predetermined, but totally exogenous. And the fact that Kristine's standing up suggests to me that she's going to take over and do the really hard part.
Okay, I feel like we should pass baton or something.
Yeah, something like that.
Okay. Hi, I'm Flannery and Hankins. So we as empiricists basically want to know what's the best tool. We have a lot of options. We also have a lot of potential problems. And so when we think about this, what I want to do is to say, we know, there we go. We know what tools are available, and we know what the literature says. There is a large literature in econometrics devoted to the consistent, efficient estimation of dynamic panels. We know that OLS has an omitted variable problem. Fixed effects addresses that, but has a short panel bias. The Ariano bond is a solution for that, but potentially has some weak instrument concerns. If you move to the Blundell bond methodology, you can address the weak instrument concerns and hypothetically improve the efficiency of the estimator. But both of those options are going to fail if we have second order serial correlation, the validity of the instruments comes into question. And so we have these newer techniques, the corrected least squares, dummy variable correction, as well as the long differencing approaches that Mark talked about. But we really know only how they perform in data sets that have been run in econometrics literature, where they have none or maybe one exogenous variable. Everything is IID. And I don't know about your data, but my data is not IID. My panels are messy. And corporate finance data in general is messy. And so what we wanted to do was say, what if we think about these problems and think about what methodologies that are available to us easily in Stata are going to best handle the features that we commonly find with corporate finance data. And so that's what Mark and I are trying to do, is deal with some of these more complicated but very common to corporate finance issues, such as multiple independent variables, things that are endogenous, variables that are co-varying or sluggish over time. How is the best way to handle this? So before I get into the details of the model, just to give you an overview of the approach we take, what we do is we are going to generate simulated data. So for each sort of feature that we're interested in, let's say it's an unbalanced panel, we're going to generate a panel that has unbalanced panels or unbalanced observations, and we're going to go ahead, create it using known parameters, known distributions of errors, and the paper goes into more detail on how we choose all those, but generate basically a panel and estimate it using the 7 different methodologies we've talked about, whether OLS, fixed effects, Ariano-Bond, Blundell-Bond, long differencing, both options, and the LSTDC. And we're going to save the coefficient estimates. We're going to generate the panel again. We're going to pull from the distribution of errors, so it's going to be different data, but we're going to re-estimate it, and we're going to do this 500 times for each sort of feature that we're interested in. And the idea is each time we're going to generate the data, save the coefficients from each type of estimation approach, and then at the end use these saved coefficients to generate a root mean squared error. That is, we're going to look at the square root of the average squared estimation error. We know what the true parameter is because we've used that to generate the simulated data. And we know from each of the methodologies what we get as the output. So what we're doing is looking at the estimation error from the true to what actually got spit out at the end, and seeing which one of these methodologies is going to be best as we vary sort of the feature of interest, whether it's an unbalanced panel or missing data and things like that. So that's what we're sort of our overall approach. Now to get into our model briefly, we're going to build off of the approach that is used by Ariano and Bond, Kvyat, very well established sort of, this is how we simulate dynamic panels in the econometrics literature. Our variation is that we are going to just layer on complications that are common to corporate finance data. That's all. And so what we have is we have a lag-dependent variable. We are going to put in multiple exogenous variables. We actually go with 7 because that mimics the example that Mark produced earlier that was on capital structure. But basically, we want to move away from just having one or no exogenous variables. That's not really realistic, I think, in our framework. We also have a fixed effect, and then we have an error term. For generating our independent variables, or our control variables that we usually put in, we are going to generate a panel structure. And this is sort of baseline. We're just going to treat these control variables, or independent right-hand side variables, as IID, very straightforward. But as we go through this, we're going to add these layers of complications and make them either endogenous or allow them to co-vary with one another, and basically try to make them more realistic to us. And then the last thing that we're going to do is be able to introduce second-order serial correlation, because obviously one of the methods that's very commonly sort of emerging in these dynamic panel estimation issues are the Ariano-Bond, the Blundell-Bond. Lots of people are using them in top-tier journals. And so the question is, we know that there is a concern about second-order serial correlation. How serious is it for our estimates. Okay, now it is, I know, early in the morning to have a lot of Greek letters up, so let's go back to sort of a more big picture approach of what we're going to talk about. The idea here is that to sort of where we're going with what we think is important for the dynamic panels, we're going to look at how does varying the panel length matter. So we're going to start with a very clean baseline balanced panel, IID errors, really nice and tidy. And then we're just going to start moving things. So we'll make that panel longer. We look at different levels of persistence in the lag. Is the lag really important to the dependent variable, or is it less important to determining what's going on in the model? We'll also think about things, sort of the structure of the exogenous variables. Are these things that covary? And this is going to turn out to be really important. The x's in our model, sort of our right-hand side, if we just treat these as IID, that's really nice and tidy. But in corporate finance, these things move together. Market to book is up. You know what? Earnings are probably a little higher. These things move in sync. And so we're going to play with those assumptions. And then we're going to move on to some very common corporate finance data limitations. We're going to think about problems on both the left-hand side and the right-hand side of the model. But we're going to think about, what if we have missing observations? Lots of us run into that. And it's not necessarily, we're not going to try to get into selection, but randomly missing observations happen. Does that cause problems? We're going to think about unbalanced panels. We're going to be thinking about dependent variable issues. So things such as clustering. We have lots of variables such as payout policy, leverage, where we have sort of a lot of firms that'll be grouped at 0. There are lots of firms that don't pay out. And that isn't necessarily explained by the things that we have on the right-hand side of the model, or firms that choose to have no debt. And we don't have all of those sort of explanatory variables in the right-hand side. So when we have these groups at 0 or whatever it is, does this clustering create a lot of problems? And then one of the other common corporate finance limitations we'll look at is censoring. Very big in capital structures, this question about whether, when we're looking at leverage ratios, a fractional response variable, how much does that affect the estimates? When you're bounded between 0 and 1, does that matter? And that's something we see in payout policy too. Whenever we have a percentage, is that going to be a concern? So we're also going to look at, if you bound your dependent variable, how does that work? And then we'll tackle the big picture, endogeneity, and second-order serial correlation. So that's sort of the story arc of where we're going to head. Oh, there we go. So all of this brouhaha, for lack of a better term, comes from the fact that we have a short panel bias when we use fixed effects in a dynamic panel. So I thought I would start off by looking at a short panel. So very easily, we're going to assume the world is IID. Life is easy. We have multiple exogenous variables and a short panel, but everything else is relatively tight. So we're going to start with a T, or panel length, of 6 for our balanced panel. And what is up here is, you'll see variations on this a couple times today. We have a dark blue bar, and that's going to represent for each of our methodologies, whether it's OLS, fixed effects, on over to LSDVC, the root mean squared error of those 500 simulations for this type of feature. So right now we're just doing IID errors and a short panel. That's all. And so we can see, not surprisingly, that our fixed effect estimator has a short panel bias on the lag, just like we would expect. And what we also see is these more advanced estimators that have been developed to address this, whether it be the LSDVC, the long differencing, the Ariano or Blundell-Bond, reduce that bias. We get better or lower estimation error when we switch to those methodologies. Moving to a slightly longer panel of a T of 12, so on sort of level with the sort of normal CompuStat data panel length. If you're looking at annual data. we see that the fixed effect estimator bias drops, as we would expect. We've gone to a longer panel, but we still see better performance from our more advanced estimators. And now we actually see the long differencing is coming in nicely too. The last thing we look at is the longest sort of panel length we'll look at is T of 30. And we chose this because there's 30 years, and people generally think that is a reasonably long panel for dealing with panel data issues. But there was a paper by Judson and Owen showing that this, even at T of 30, there still is a dynamic panel bias, short panel bias. And so we wanted to make sure we went out that far and looked at that also. And what we find is fixed effect estimators are getting much, much better. Their accuracy is improved dramatically. But our advanced estimators are still performing better. And so we see LSDVC, blood bond, all of those, all are basically negligible bias. Now what we've done so far has been talking about almost exclusively the root mean squared error on the lag dependent variable. And we haven't looked at all, or I haven't said anything, about the bias on those x's. So each one of these light bars across the figure represents the average root mean squared error for the 7 independent variables we're including in this model, which right now are all IID. And they have very little bias. It looks very nice. We have very little estimation error. So if we go back just to refresh, even with a T of 6, the estimation error on these, the average x's, is pretty small. But IID assumptions really probably are not necessarily that useful for corporate finance purposes. So what we want to do is try to think about whether or not we can create a more realistic panel data structure. And the way we went about doing this was to actually think about using a variance-covariance matrix from CompuStat data. And so we looked at EBIT, market to book, size, very common corporate variables. Granted, is that what everybody uses? No. But is it indicative of some common features? We hope it's somewhat representative. And we've used that variance-covariance matrix of the residuals and actually use that to generate the errors for our panel innovations. And let's see what happens. We switched from IID to our CompuStat style errors. And you can see the root mean squared error on the lag dependent variable performs pretty well, same as before. However, there's a little bit of a disturbing trend on those the x's. Obviously, we see a huge jump. And this, while sort of if you say, okay, what's my best approach? Before LSDVC performed well, it still continues to perform well. Great, but I don't think that's going to be very comforting if you're actually trying to interpret anything about these x's. The root mean squared error is enormous. So what's changed? Just to sort of show you the mechanics here. I've shown you a really scary root mean squared error that is a huge estimation error across a large number of simulations. But what did we actually do? What we did is all that's changed is the errors on that panel construction of the right-hand side variables. So our independent variables no longer are evolving with an IID process, but we're pulling from this CompuStat-based variance-covariance matrix. This allows us to do two things. One, it allows the variables to co-vary together. And I think that really is an important feature here, is recognizing that these are not necessarily independent variables completely. And then the other thing that's kind of interesting is that the size of our error term varies a lot. And this is something I hadn't really focused on until we started working on this project. But these variables that we use in CompuStat, some of them move around a lot, very nicely behaved, but some of them are very sluggish. They're almost time invariant, but have very little within firm intertemporal variation. And when you have these incredibly sluggish variables, they're hard to estimate. And it's one of these things that, so you think about it, and intuitively it makes sense. It's in every econometrics book, but at least when I was taking econometrics, it really wasn't drilled into me. If you have sluggish variables, things that are not moving a lot over time, and then you attempt to control for unobserved heterogeneity, it is really difficult to estimate those sluggish variables. And so the paper goes into more detail, but just to give you an idea, we have 7 exogenous variables on our right-hand side. Looking at those individually, if I plotted the variance of those sort of over time against each one of their individual root mean squared errors that I get across these simulations for a short panel, if I have sort of some reasonable level of variation over time, I can estimate, no problem. However, when you get to very low levels of variance, which some of these variables have, the root mean squared errors explode. And this isn't really sort of the focus of the paper. The paper is sort of a dynamic estimation choice. But this really just stood out as an interesting sort of side note for us. How, when you're doing these dynamic panels, estimating these sluggish variables is incredibly difficult and should be undertaken with real caution. So we looked at the short panels with the CompuStat innovations that is moving away from IID. If we look at a slightly longer panel of a T of 12, again, those root mean squared errors have come down. LSDVC still is our best approach, but these are still very concerning for anybody that is interested in interpreting the coefficients on any of these right-hand side variables. You have a huge amount of estimation error. And even moving to 30, again, lower errors, but they are still non-trivial. And so this issue of when you're dealing with corporate data, things that are co-varying together or may have low levels of intertemporal variation, you're going to have increased estimation error. And so that's something to sort of keep in mind. So we're going to move on to more common data limitations that are found in corporate finance. For all of these simulations, we're going to just basically limit ourselves to a T of 12, that is sort of our medium length panel, and we're just going to look at data where we use these CompuStat innovations. We know most of these behave relatively well. The methodologies behave relatively well when everything is IID and tidy, but we're not sure that that's really necessarily representative for most of our empirical work. So to think about these limitations, on the one side, we want to think sort of on the right-hand side, whether we have panel imbalance, and to mimic that, so we have an average T of 12, but we set half the panels to a T of 6 and half to T of 18, so the average is in between. We then think about missing data, and we do this by just randomly deleting 10% of the firm year observations. We look at the dependent variable censoring and clustering. For the censoring, all we do is go ahead, and as I said, we don't want to get into selection issues. That is its own econometrics literature unto itself. But if we have sort of random censoring where firms are doing this and it just isn't captured by our right-hand side variables, we go ahead and just randomly 10% set of their dependent variables to 0 to capture that clustering. And then the censoring, we're just going to Windsorize. We're bringing the tails about 4% on each end, and that is in line with what we see in capital structure as far as having some bounds on our dependent variable. So we think we've taken some attempt to get these to look like real corporate finance data. When we look at unbalanced panels or missing observations, basically if we have limitations that are on our right-hand side, least squares dummy variable correction seems to do the best, but Blondel-Bond is nice. When it's on the left-hand side, The Blundell-Bond is the best estimator, but the least squares dummy variable correction also performs well. So both of them are doing pretty well. There's sort of some preference depending on the type of issue you have, but they both do reasonably fine, within the bounds of the fact that we still have these sluggish variables and all that noise. The problem is that each of these approaches has very well-known shortcomings. So for the LSDDC, it's assuming everything on the right-hand side is exogenous. And I'm pretty sure that's not true if you're dealing with corporate data. And then if you're dealing with Blundell-Bond, that relies for the validity of the instruments that you have no second-order serial correlation. And anybody that's run Blundell-Bond and looked at those tests that come after it on data will realize that's a pretty hard threshold to cross. So each of these has an issue, but the question is, how serious are these? You know, maybe, okay, it's not ideal, it's not exactly what was derived in theory, but maybe it still is our best choice. And so that's what we look at next. So to induce the endogeneity, we follow the Wintocki paper, which is the 2012 JFE, and make our X's dependent on both the lag-dependent variable as well as the fixed effect. So basically, those are going to be, we think about low endogeneity as well as high endogeneity by varying those alphas and making it sort of more or less endogenous. And we go ahead and actually test these just to make sure that we're inducing what we want to induce as far as the endogeneity using the Wooldridge test. I don't know if everybody's seen this. But Wooldridge has a test where it basically builds on the idea that your future values should not predict the current outcomes if you do not have endogeneity. And so sort of setting that up, if you put future values of your X in your baseline specification, they should have no predictive power. Well, when we do that with our endogenous variables, at the low level we see that some of them do, and when we go to our high level, all of them do. So we feel like we're inducing endogeneity in our simulations. Okay, so just as a refresher, we're going to be, this has no endogeneity. This is our CompuStat innovations with a panel of 12. And this is what the errors look like. When we induce low endogeneity, what we see is, not surprisingly, LSDDC, which is supposed to not do well with endogeneity, has an increase in its root mean squared errors for the endogenous variables. We also interestingly find Ariano-Bond is basically horrific with endogenous variables. The root mean squared error just absolutely explodes. And this fits actually with the literature. Blundell-Bond in their original 1998 paper, while they were pointing out some of the issues with Ariano-Bond, noted that AB had really low precision power as well as finite sample bias when it was dealing with weakly exogenous variables. Moving to fully endogenous, obviously we're going to see that blossom. What we do find is that Blundell-Bond and our very much maligned fixed effect estimators do pretty well. And it really depends what your coefficients of interest are. If you're interested in the lag-dependent variable, Blundell-Bond is slightly better. If you're interested in those exogenous or independent variables, or I guess not in exogenous, but our independent variables, whether they be endogenous or exogenous, fixed effects estimates are actually slightly better. So this is just at a low level of endogeneity. When we switch over to the high level of endogeneity, again, we see Ariano-Bond is a mess. We see the bias on, or the estimation error on the least squared dummy variable correction inflates, as we would expect from theory, and that fixed effects and Blundell-Bond remain our best choices. Okay, I'm not going to go too many more of those tables, but just to give you an overview, we then extend with these endogenous variable frameworks into the corporate finance limitations we talked about before of missing data, unbalanced panels, all of those things, the dependent variable clustering and censoring. And what we find is really interesting. If you have an unbalanced panel, well, at least the way we've structured it, where half of the T's are 6 units long, half are 18. So that level of unbalance, if you have endogenous variables, do not try to estimate them. These short panel issues, you are just not going to have valid instruments, and the LSDVC, where you're not relying on instrument validity, is less useful on the endogenous variables, and really all you're generating on those variables is noise. I mean, the level of root mean squared error is off the charts, and I found this absolutely interesting. It really was, in these shorter panels, it was just noise. If you're interested in the lag-dependent variable or the exogenous variable estimates, you can do better, but really only if it's a less persistent panel. So if that lag-dependent variable is really important to next period, sort of as that approaches the unit circle, you're not going to be able to estimate efficiently. So there's lots of problems when you have endogeneity and very short panels. Going on to the more other issues we've talked about, this is all back to a balanced panel of T of 12. Missing data, nothing serious about it. You can deal with it. Blundell bond is the best. Fixed effect also is a nice estimate choice. Censoring, the same thing. With the clustering, actually, the fixed effects outperforms the Blundell bond. And I think this is just absolutely fascinating. But there are times where fixed effects is your best choice. And of course, this is only tested on a balanced panel. So imagine you have both clustering and an unbalanced panel. You would really have to weigh sort of which one is sort of the bigger concern. Is your degree of unbalance very large or what? And go from there. And then the last layer that we wanted to add on to this was the second order serial correlation. So far, basically the takeaways have been, if your data is, if everything's exogenous, LSDVC really does nicely, with Blundell bond being a great second choice. When you move into the world with endogenous variables, you have to be really worried about shorter panels, but Blundell bond does pretty well, and fixed effect seems to be a great second choice. But the Blundell bond still relies on this assumption that second order correlation doesn't exist. Well, how important is that? So we modify the error term, and these are parameters that were chosen based on sort of things that are in line with capital structure data. And we look at how the second order serial correlation matters when you have no endogeneity, lower levels of endogenous variables, and higher levels of endogenous variables. So across this spectrum. And what we see is that, so just to look at the low endogeneity situation, we have pretty decent, actually, estimates for the Blundell bond estimator. And this is surprising. So this is low endogeneity. There is second order serial correlation, much akin to what we would find in a capital structure panel or anything else. And while this is not perfect estimates, Blundell bond is one of our better choices. Fixed effects also does well, but sort of your preference is it's not as bad as we would think. Sort of interesting. The other takeaways from our second order serial correlation tests were that with no endogeneity, LSDVC still is our best choice. So that matches the earlier work when you don't have endogenous variables, LSDVC can be a go-to good choice. Blundell bond, not actually terrible with a reasonable level of second order serial correlation. And then the other really sort of bizarre thing was that the reason the long difference estimators were created was to get around second order serial correlation. They actually don't do as well as the Blundell bond, at least with this level of second order serial correlation. Now, we haven't tried every sort of variation there, but I found that that was an interesting kind of takeaway. Okay, so conclusions, leaving plenty of time hopefully for questions. hopefully we've convinced you that the econometrics are important here and that you're going to get a lot of variation on those estimates, and that trying to think about what features of your data you can figure out, whether it's missing data, unbalanced panels, do you have endogenous variables or second order series correlation, can help you figure out the best way to estimate those panels. There were a couple things that popped out to me just as far as really sort of cautionary notes. One was ignoring the short panel bias is going to cause huge problems. The second one was these sluggish variables, the ones where you don't see a lot of intertemporal variation, are incredibly difficult to estimate when we're trying to control for unobserved heterogeneity. And then the last one that I found incredibly surprising was how poor the Ariano bond estimator did in the presence of endogenous variables. And just to sort of reiterate that there is this Wooldridge test, we have it on the website we've set up, but just Wooldridge basic econometric textbook sort of explains how to test for endogeneity, and that's sort of probably going to be a useful vetting technique. And so our takeaways are that the best choices without endogenous variables seem to be LSBVC and the Blundell bond, and that when you are faced with endogeneity, sort of the go-to choices are the Blundell bond and the fixed effects estimator. So, thank you very much for getting up at 8:30 to learn about it a little bit over. And I think if you have any easy questions, I'll take those, and Mark will take any of your hard ones. Yes.
In corporate finance, we do have heterogeneity, and the standard that we see in all the many papers is fixed effects.
Yes.
So, first takeaway I get from this presentation is that we are doing this fine with fixed effects.
Sorry,
We're
with
doing fine with fixed effects.
With the common fixed effects estimator.
yes, with the common fixed effects estimator. Yeah, with the low levels of endogeneity, it actually doesn't look that bad. Now, clearly, the fixed effects estimator has issues depending on the level of imbalance in your data. But it is interesting that we spent all this time worrying about the correlation between the transformed lag and the transformed error, and it really doesn't look like, when you throw in basically all the other confounding factors, that it really is the biggest problem we have.
Kristine, the way I see this, maybe I'm completely wrong, is that we have introduced the time series within the panel, right? So the time series has non-stationary, and we're trying to take out the non-stationary by having first order or second order of these lag effects of dependent variables, right? Now, each firm has their own way of what is the serial correlation, right? One firm may have one is going to take care of it, the other firm may have two will take care of it, but the other firm may be the long distance, right? So then you kind of like taking the average, what is the average of the distance that I need to take for my firm in my sample, am I correct?
You
on
said
this?
for the
When you do the second order or third order, whatever is best, right? That give you the mean error the least, that give you the least bias. It depends upon what the sample firm in my sample is, and whether that sample firms, okay, they have only on average only one first difference, will take care of it. Oh, the other is two difference, will take care of it.
You're saying the process associated with different firms differs.
Right.
Right?
That's correct.
And if that's the case, then, which it probably is, a different set of estimations would be useful, and simulations would be useful to figure out how destructive it is to impose a constant adjustment speed, say, on firms with substantially different adjustment speeds. And we didn't do that. We didn't get into that. But I think that maybe a bigger implication, or more specific implication of what you're saying is, I was talking to Arthur Cordovay from Stanford last week when he came to give a paper in Florida. And I said that I thought that trying to estimate a partial adjustment model across all CRISP-CompuStat firms was really a bad idea. Because in fact, the adjustment depended a lot on it was very conditional on where firms were in important other dimensions. So I think that observation opens a range of interesting and difficult issues associated with making big estimates.
I couldn't agree more. I mean, and there has been a move in the econometrics literature to heterogeneous panel estimation, where they're looking at the slopes separately for each firm. And so that would get at some of what you're saying.
And SPC, we don't have the estimation of blend of bond. We can use XT bond 2 on the estimator, and then we'll take care of it.
Yeah, there's the XTA bond 2, but as well as that was a user-written command, and they have now incorporated that in like the more recent versions. It's XT DPD sys SYS, and that has all the same features, but is actually sort of vetted by Stata. And it's not anything against the user-written commands. A lot of us use them, but sort of it's nice to know that that's the hypothetically final version.
So when you use a random form or random bound estimator, there's a decision to be made how many legs you use.
Yes.
In your simulation, you use all the legs available, or just fix some number of legs?
That's a great question. I don't know if everybody heard it, but when you execute these Ariana bond, Blundell bond, just from Stata CAN commands, you have a choice on how many lags to use. And there are two places that you can choose lags. So you can actually put in their models in Stata multiple lag-dependent variables if you'd like. But the other part, and really I think the more important part for most of us, is just how many lagged instruments do you want to incorporate. So for our simulations, we went with the Stata defaults, not because that we per se agree that they are the best choice, but just if somebody's going to pick up this paper and say, okay, let's use Blundell bond, plug it in their computer, and that's the last they think of it, that was sort of our approach. But there is sort of this debate within the literature on the number of lags, and there's sort of how many lags. If you have too many lags, that can be very concerning. If you have too few lags, that was the Anderson and Sorensen paper, too few lags is just as bad as too many lags. And so I think that one of the things that we take away, especially sort of going back to the original question of is fixed effects okay, is it may be useful to try a couple different things and see how consistent the estimates are.
This in your simulations taking all the legs?
So let me specify, for Ariana bond, the default is to use one lag. That's what we used. And for Blundell bond, it is T minus P minus 2, I think, which is basically your panel length minus your number of lags minus 2. And I think we went with the lowest for our short panel, and so it would be 3 lags. Yes?
I have a question concerning the time indicator of my panel. For instance, most computer data and so on has annual data, but what happens when your time indicator is basically a corporate event, like an acquisition, which in series has sometimes a company makes acquisitions only once a year, but others make 3, 4, 5 acquisitions a year, up to 100 in the total sample. And the time indicator is then the acquisition event. How do you deal with that problem?
Well, if you just have time dummies, right, and your event indicator varies across your sample, that's going to be okay, because your time dummy is going to suck up your macro level changes, and your event indicator is going to vary. What also is interesting, I don't know if you've seen this paper, is the Bertrand, Dufflo, and Mullinathon. It was an old different paper, right? But it talks about when you have things that sort of switch on and switch off as far as indicator variables, how to deal with the standard errors. It's not a dynamic panel paper, but if you're interested in that, it might be interesting. It's more different. It's definitely a different paper.
QJE early 2000s.
Yeah.
I think.
Sounds right. Anybody on the site?
QJ,
Thank you. You get it? Yes, sorry.
Is your conclusion affected by the sample you employed? I guess my question is related to his question. So what I'm saying is just so happen that BP model fits your data better than the other model. If you employ a different sample or subsample even, you could come up with a different conclusion or a slightly different conclusion.
Well, so I absolutely agree. That sort of this is based on one set of one variance covariance matrix. It's based on us when we present these results. We are averaging across our exogenous variables or our endogenous variables, and so the weighting can definitely skew it. But I think what we've been able to show are things that are very much consistent with the underlying theory. So the fact that the sluggish variables are hard to identify, that the length of the panel matters very much. And so this, what we also found is that some of the common corporate finance locations, such as the unbalanced panels, stuff for fixed effects, but the missing and things like that, don't have as big of an effect as we would think. And that actually does fit with some of the literature, like the Popke and Woodruff paper, that sort of fractional response variables can be estimated with linear models and things like that. So I am definitely sensitive to A, the way we present it, as well as the underlying assumptions are going to matter. But I hope that our paper is reasonably transparent enough that you can pull out the pieces that you would find would be relevant. Mark, do you have any other?
Well, it's surprising when you get into this sort of study, how fast the possibilities expand. You know, what could we look at? So one of the things I was very curious about was looking at the line lengths, as you suggested, and you just have to call stops at some point and say, here are some results. They're conditional on the sample we're using. We have no reason to believe the sample that we used of the CompuStat variables is special, but we don't know beyond that. So there are lots more questions left beyond the ones that we think we provided some sort of answer to.
Yes.
Thank you very much for your interesting presentation. You mentioned in your, if I fully understand, the output of your research is that BB is the best one, because it is present with or without homogeneity. That is blunder and
The blood of one.
which is the best one.
It seems to be the
according
most.
to your research. So I am really interested for sludge variables case, which is my case in my research. You mentioned that BB is the best if the dependent variable is censored or clustered. That is the Y. The research interest is the Y. In my case, the research interest is X. And X is sometimes censored, sometimes clustered, and clashed and sluggish, do not vary over time. So,
What do I do? Okay, so the first two I'd say, okay, well, you know, sometimes it's censored, sometimes it's sluggish. There are ways you can think about.
Excuse me, because in your, it seems that in your framework, that the mean interest is the Y. Because
Yes.
in most capital structure literature, the Y is, the debt ratio is in the Y. Whereas there is other equation in corporate finance where the interest is the X.
Yes.
What if?
Absolutely. I think we have not focused as much on sort of transforming those X's or thinking about limitations on the X's besides sort of the missing observations and things like that. What I would say is when I heard sluggish, it was sort of the flags went up. And that would be something, I think, regardless of how much digging you do, if you're trying to control for the unobserved heterogeneity and you don't have a lot of time variation in your variables, you're going to have to really sort of think about how you're going to estimate those. And it's not as if a random effects estimator is going to be your go-to choice, because in quasi-demeaning your data with a random effects estimator, you're still going to run into the short panel issue where you have correlation between the transformed lag and the transformed error. So that's not really the necessary solution.
So,
Yeah.
So you base on the judgment about the quality of this estimate in root mean square.
We also did, what was it, mean average error? We did it in May.
mean absolute error.
Mean absolute error.
That's about the error of those coefficients across the simulations.
Yes.
And how about the bias? Because I thought that is kind of how accurate you have that. But the other thing I
Yes.
was the bias.
Yeah, I tried to correct myself the few times I said bias. I was not trying to imply a direction.
Yeah.
We know that the OLS estimates on the lag are upward bias. We know that fixed effects estimates on the lag are downward bias. The paper goes into a little more detail because we do actually present sort of what percent are over or under the coefficient of interest, sort of the direction and the skew, basically skew of the variable. But we didn't do that throughout the tables. Basically, it was just sort of getting overwhelming.
Because the problem is I could estimate something more accurately with more error as more standard deviation, but
Absolutely.
if the direction is wrong, then yeah.
And some of the tables we have in the paper do have information about that.
Yeah.
So, but probably not enough to answer all your questions.